Hey everyone, welcome back for another deep dive. Today we're taking a crack at Unsolved Problems in Astrophysics, a book that dives into the biggest mysteries that are keeping scientists, well, scratching their heads.
It is, yeah, kind of a collection of all the big questions in astrophysics right now.
Yeah, so we'll be looking at everything from the expansion of the universe to some really strange things happening right here in our solar system. I think there's something here for everyone, whether you're a seasoned space enthusiast or just, starting to get curious about the cosmos.
Yeah, I think one of the cool things about these mysteries is they touch on things that, affect us here on Earth
Yeah.
and things that affect the fate of the universe, so.
Okay, so let's jump right in. First up, dark energy and dark matter. I think it's safe to say that these two have kind of like revolutionized how we see the universe, right?
Absolutely. I mean, imagine the universe is like a loaf of raisin bread that's baking in the oven.
Okay, I can see where this is going.
As the bread rises, the raisins move farther apart.
Right.
That's like the expansion of the universe. But here's the thing, with dark energy, it's like something is making the dough itself expand even faster
So it's pushing those raisins away even faster.
at an accelerating rate.
Exactly.
And it's thought that this mysterious force makes up about 70% of the universe's total energy. So it's a big deal.
Yeah. That's crazy. So it's not just that things are moving apart, but like the space between them is actually growing at an increasing speed.
That's right.
That's a pretty wild concept to get your head around.
Yeah, I remember when I first learned about it. It was a mind bender for sure.
I remember reading that this discovery really like shook things up in the late 90s, right? Like scientists were expecting the expansion to be slowing down because of gravity, but then
They found out it was speeding up, and that was a huge surprise. And that's kind of how dark energy entered the scene.
yeah, threw a real wrench into our understanding.
Yeah, for sure.
So what are the leading theories then about what this dark energy actually is? I know there's this idea of a cosmological constant and something called quintessence. Can you break those down a little?
Right, right. Those are like the two main contenders right now. The cosmological constant, it's like the energy of empty space itself.
So even nothingness has energy.
Yeah, which is a pretty wild thought.
Yeah.
Right.
Yeah.
But and this constant energy would provide that outward push, causing that accelerated expansion we were talking about. The other possibility is quintessence, which proposes a more dynamic energy field, one that changes over time
Okay.
and interacts with gravity in a way that could also lead to the acceleration we see.
So is it like, I'm trying to visualize this in my head. Is it pushing on space or is it like pulling or I don't even know.
That's a great question. It's more like it's woven into the fabric of space itself, and it's kind of stretching that fabric,
Okay.
causing everything to move apart.
Okay, I think I'm starting to wrap my head around it.
Good, good.
But if this dark energy keeps accelerating this expansion,
Mm-hmm.
what happens like eventually? What does that mean for the fate of the universe? Are we talking like the big freeze or the big crunch scenario?
That's the $1 million question, and it really depends on the nature of dark energy, right? Whether it's constant or whether it's changing. If it's the cosmological constant and keeps pushing outward, then we might be headed for the big freeze, where the universe expands forever, becoming incredibly cold and spread out.
So like all the stars would eventually burn out, galaxies would drift apart.
Yeah, just kind of an empty and lonely place.
Mhm.
Or, if dark energy behaves differently, it could lead to the big crunch,
Right.
where everything kind of collapses back in on itself due to, gravity eventually winning out.
Like a cosmic rewind.
Exactly.
But there's more to this dark energy than just the fate of the universe, right?
Yeah.
I've heard it might have played a role in like forming the very first galaxies.
Yeah, you're right. There's growing evidence that early dark energy, which might have been, much stronger in the early universe, could have influenced how matter clumped together,
Yeah.
leading to those first galaxies and the large scale structure we see today. So we're not just talking about the future; we're talking about the very beginnings as well.
Wow, so this invisible force could be shaping the universe at both ends of the timeline.
Yeah, that's the amazing thing about it.
Okay, so we've tackled dark energy. Now let's move on to its equally enigmatic partner, dark matter. This stuff makes up a whopping 85% of all the matter in the universe, but we can't see it. So how do we even know it's there?
It's a great question. And the answer lies in its gravitational effects.
Okay, what do you mean by that?
It's like watching a shadow puppet show, right? You see the shadows dancing on the screen, but you don't see the puppets themselves.
Okay, yeah.
So we see the effects of dark matter. We see its gravitational pull, but we can't directly observe the matter itself.
So what are some of the ways we see those effects then?
Well, take galaxies, for instance. They're rotating much faster than they should be, based on the amount of visible matter we see.
Okay.
It's as if there's like some invisible stuff providing extra gravity to hold them together, you know?
Preventing them from flying apart.
Exactly. And that stuff is what we believe to be dark matter.
Okay.
And that's just one example. There's also evidence from the way light bends around galaxy clusters.
Oh yeah, gravitational lensing.
Exactly, gravitational lensing. It's like looking through a warped piece of glass. The light from distant objects is distorted and magnified, and this distortion tells us there's more mass there than we can see.
So again, dark matter to the rescue.
Yeah, to explain that discrepancy.
Okay, so we've got all this evidence, but what are the leading candidates for what it could actually be made of? I've heard of WIMPs and axions.
Right. Those are two of the most popular suspects. WIMPs, which stands for weakly interacting massive particles, are hypothetical particles that are much heavier than protons, but interact very weakly with normal matter, making them incredibly hard to detect.
So they're kind of like ghosts almost, passing through everything.
Exactly. And then you have axions, which are much lighter particles that could potentially be detected through their interaction with electromagnetic fields.
So we're talking about a whole new category of particles, basically.
Yeah.
That don't behave like anything we've seen before.
Right.
But it gets even deeper, right? Because now there's research suggesting a connection between dark matter and supermassive black holes.
Yeah, that's one of the most exciting new developments in the field. Some researchers are proposing that dark matter might not just be passively influencing galaxies, but it might actually be interacting with those supermassive black holes at the centers of galaxies. And these interactions could even be producing some of the high energy particles and radiation we observe coming from those regions.
Whoa. So we've got two cosmic mysteries potentially intertwined.
Exactly. And it's getting really complex and really interesting.
This is getting pretty heavy. But I guess that's what makes it so fascinating. Each answer seems to lead to even more questions.
Yeah, it's a never-ending journey of discovery.
Speaking of questions, let's move on to another big one that has to do with the very building blocks of our universe. The matter-antimatter imbalance.
Ah, yeah. This is a classic.
So, according to our understanding of the Big Bang, matter and antimatter should have been created in equal amounts in the early universe.
Right.
But obviously something went wrong.
Yeah.
Because we're here.
Exactly.
And we're made of matter, not antimatter. Where did all the antimatter go?
Yeah, that's the big question. It's like the ultimate vanishing act, right? So the prevailing theory is that in the very early universe, some subtle difference in the laws of physics led to a tiny excess of matter over antimatter.
Okay.
And as the universe cooled and expanded, most of the matter and antimatter just annihilated each other, releasing this huge amount of energy. But that tiny excess of matter survived. And that's what formed all the stars and galaxies and planets and us.
So it's like this cosmic game of musical chairs where matter snagged the last seat.
Exactly. Exactly.
It's incredible to think that such a tiny imbalance could have such enormous consequences.
It is. And to understand what might have caused this imbalance, scientists are looking at these tiny elusive particles called neutrinos.
Neutrinos, okay.
Yeah, neutrinos and their antimatter counterparts, antineutrinos, they might hold the key to unlocking this mystery.
Right.
If we can find even subtle differences in their behavior, it could revolutionize our understanding of the fundamental forces that shape the universe.
So these tiny particles might hold the answer to one of the biggest questions in cosmology.
Yeah, it's pretty amazing when you think about it. And what's even more fascinating is that this whole mystery of the matter-antimatter imbalance could point to new physics, beyond our current understanding.
Like we need to rewrite the rules a little bit.
Maybe.
That's what I love about astrophysics. Every discovery just opens up a whole new world of possibilities.
Yeah, it's a really exciting field to be in.
And speaking of big discoveries, let's talk about the Big Bang itself. It's the prevailing theory for the origin of the universe. But it still leaves us with some pretty big questions.
Oh, absolutely. I mean, The Big Bang Theory explains a lot. The expansion of the universe, the cosmic microwave background radiation, the abundance of light elements, but it doesn't answer everything.
So what are some of those big unanswered questions?
Well, one of the biggest ones is what caused the Big Bang in the first place?
Yeah.
What triggered this sudden expansion from a state of, unimaginable density and heat? And what, if anything, existed before the Big Bang?
Yeah.
I mean, these questions push us to the very limits of our current understanding. We're talking about the origin of space and time.
That's a pretty tough one to tackle.
Yeah, it is.
We've been talking about these universe-scale mysteries, and it just occurred to me that not all cosmic puzzles are, way out there in the distant reaches of space. We've got some pretty intriguing enigmas right here in our own solar system.
You're absolutely right. Sometimes we get so caught up looking at the grand scheme of things that we forget about the mysteries in our own backyard.
Yeah, exactly. So let's bring things a little closer to home then. What are some of the solar system mysteries that have you scratching your head?
Well, one that always comes to mind is Saturn's strange rotation rate. We usually figure out a planet's rotation by tracking features in its atmosphere, like cloud patterns.
Yeah, like Jupiter's Great Red Spot.
Exactly, yeah. But with Saturn, the rotation rate we get from its magnetosphere, the region dominated by its magnetic field, doesn't match up with the rotation rate we observe in its clouds. It's like different parts of the planet are spinning at different speeds.
That sounds like a recipe for some serious cosmic dizziness.
Yeah, it does. And scientists are still trying to figure out what's causing that kind of discrepancy.
So is it possible that it's like something deeper inside the planet?
Yeah, it suggests that Saturn's deep interior, hidden beneath those swirling cloud layers, might be rotating at a different rate than its outer atmosphere. It makes you wonder what's going on beneath those beautiful rings.
Yeah. What secrets are lurking beneath the surface? Okay, so Saturn has some strange rotational quirks, but our own star, the Sun, isn't without its mysteries either. I'm talking about the solar cycle, the Sun's 11-year heartbeat of activity that's, marked by changes in sunspots and solar flares and all sorts of other energetic outbursts. We can observe these changes, but what's actually driving them?
That's another great question. We know the solar cycle is tied to the sun's magnetic field, which flips every 11 years, but the exact mechanisms behind this magnetic flip-flop are still being debated.
So is it like trying to understand the inner workings of a giant complex dynamo?
That's a good analogy.
Okay.
Yeah.
And this isn't just an academic puzzle, right? Understanding the solar cycle has real world implications because those solar outbursts, they can impact us here on Earth.
Absolutely. Those bursts of energy from the sun can disrupt satellites, communication systems, even power grids, causing all sorts of havoc. The more we understand the solar cycle, the better we can predict these events and safeguard our technology and infrastructure.
Yeah, you don't want to be caught off guard when the sun decides to have a little tantrum.
Yeah, exactly. And while we're talking about solar surprises, there's another one that's been baffling scientists for a long time.
Yeah.
The corona mystery.
Oh, yeah. Explain that one.
Okay, so the corona. It's the outermost layer of the sun's atmosphere, and it's incredibly hot, millions of degrees Celsius.
Wow.
Much, much hotter than the sun's surface.
Oh, it's like stepping away from a campfire and finding yourself in a blast furnace.
Yeah, that's a good way to put it. This defies basic thermodynamics because you'd expect things to cool down as you move farther away from the heat source.
Yeah.
But the corona, it throws that logic right out the window.
So we've got a star that throws unpredictable tantrums, has an atmosphere that's hotter than its surface.
Mm-hmm.
Sounds like the sun is kicking us on our toes.
Yeah, it does. But you know what? Compared to our next mystery, the sun almost seems predictable.
Okay, bring it on. What we got?
Get ready for this. Fast radio bursts, or FRBs for short.
Okay, I've heard of these.
Imagine a millisecond long burst of radio waves, incredibly bright, coming from a distant galaxy billions of light years away.
Wow.
That's an FRB. They were only discovered in 2007, and we're still scratching our heads about what's causing them.
So they're like cosmic Morse code messages from who knows where.
Yeah, Exactly.
Any theories about who's sending these signals?
We've got a whole lineup of suspects ranging from the exotic neutron stars, black holes, even the collapse of these hypothetical particles called axion stars to the incredibly speculative like dare I say it extraterrestrial signals.
Whoa, hold on.
Yeah.
Alien signals.
Well, it's certainly one of the more intriguing possibilities, but we need a lot more evidence before we can, jump to any conclusions.
Yeah.
The truth is we're still in the early stages of understanding these FRBs. They're one of the newest and most baffling mysteries in astrophysics, and they're a reminder of, how much we still have to learn about the universe.
It's both humbling and exciting, isn't it, to realize that even in the 21st century, we're still surrounded by so much cosmic wonder.
Absolutely. It's a great reminder of how much we don't know and how much there is still out there to discover.
But hey, we're just getting started with our deep dive. There are many more unsolved mysteries to unravel, and I can't wait to see what other surprises the universe has in store for us.
And speaking of those surprises, let's shift gears a bit and talk about a cosmic curveball that's been causing quite a stir in the astrophysics world,
Okay.
the Hubble tension.
Okay, I've heard about this, but to be honest, it always sounded a bit technical to me, like
Yeah.
something you'd need a PhD to understand. Can you break it down for us? What's the Hubble tension all about, and why should we care?
Yeah, happy to demystify it for you. So, the Hubble constant is this crucial number that tells us how fast the universe is expanding right now.
Okay.
It's like the speedometer for the cosmos.
Okay.
The problem is we're getting different speed readings depending on how we try to measure it.
So it's like using two different rulers to measure the same piece of fabric, or
Exactly.
getting two different lengths.
Exactly. On the one hand, we're looking at the afterglow of the Big Bang, the cosmic microwave background radiation. That gives us one value for the Hubble constant. But then we have these incredibly bright exploding stars called supernovae, which give us a different value. And the difference isn't small either. It's enough to make scientists question whether we're missing something fundamental about our understanding of the universe.
So this seemingly simple number, the Hubble constant, could actually be a sign that our current model of the universe needs an upgrade.
That's a possibility.
That's pretty mind-blowing.
Yeah, it's a real puzzle, and scientists are exploring all sorts of ideas to try to explain it.
So what are some of the theories out there?
Well, some scientists are proposing that there might be new physics at play, something we haven't discovered yet that's affecting the expansion rate. Others are looking at whether our understanding of dark energy needs to be refined. There's even speculation that it could point to the existence of extra dimensions. It's a real cosmic detective story, and the clues are leading us in some very exciting directions.
It just goes to show that even in a field as advanced as astrophysics, we're still constantly learning and revising our understanding of the universe. Okay, so we've tackled this speed limit problem. But what about the universe's overall size and shape? I remember looking up at the night sky as a kid and just being awestruck by its vastness. What do we actually know about the geometry of the universe?
It's a question that has fascinated humans for centuries. And based on our observations, the universe appears to be very close to flat, at least on the largest scales.
Flat. I always pictured it more like a sphere.
It's a common image, but imagine a flat sheet of paper extending infinitely in all directions. That's the closest analogy to our current understanding. Of course, we can only observe a limited portion of the universe, the part that light has had time to reach us from.
Right.
It's like we're looking at a tiny patch of that sheet of paper and trying to extrapolate its overall shape.
So even with all our advanced technology, we're still limited by the speed of light.
Exactly. And while the observable universe is incredibly vast, billions of light years across, we don't know for sure whether the entire universe is finite or infinite. There could be a whole lot more out there beyond our cosmic horizon.
Wow. It really puts things in perspective. Okay, so we've talked about the universe's shape and size, but what about the force that governs it all, gravity? It's the force that keeps our feet on the ground, but it also shapes galaxies and holds the cosmos together. And yet it seems like gravity is still one of the biggest mysteries in physics.
You're absolutely right. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by mass and energy. And it's been incredibly successful in explaining phenomena like the bending of light around massive objects and the orbits of planets. But general relativity doesn't quite mesh with quantum mechanics, the theory that governs the world of the very small men, the world of atoms and subatomic particles.
So we've got these two incredibly powerful theories that work perfectly in their own domains, but they don't play nice together.
Exactly. And that's a big problem because there are situations in the universe where both gravity and quantum mechanics are at play, like in the very early universe or inside black holes. So physicists have been on a quest to find a theory of quantum gravity, a theory that could unify these two pillars of modern physics.
It's like we're searching for the missing link in our understanding of the universe.
In a way, yes.
But I guess that's part of what makes science so exciting. There are always more frontiers to explore. And speaking of exploration, I can't resist bringing up the biggest quest of all. The search for extraterrestrial life. Are we alone in the universe? It's a question that has fascinated humans for as long as we've looked up at the stars.
And it's a question that's becoming more and more relevant as we discover more and more exoplanets, planets orbiting other stars. We now know that planets are incredibly common in the Milky Way galaxy, and many of them lie within their star's habitable zone, where conditions might be just right for liquid water to exist, and where life as we know it could potentially thrive.
So the real estate market for potentially habitable planets is booming.
You could say that.
But finding a planet in the habitable zone is just the first step, right? There's a lot more that goes into making a planet truly suitable for life.
Absolutely. We need to consider factors like the planet's atmosphere, its magnetic field, its geological activity, and a host of other factors that could make it hospitable or hostile to life. And even if a planet ticks all the right boxes, there's still no guarantee that life has actually emerged there.
So it's a long shot, but the potential payoff is huge. Imagine the impact on humanity if we were to find definitive proof that we're not alone in the universe. It would be a game changer, wouldn't it?
It would completely revolutionize our understanding of our place in the cosmos. It would force us to reconsider everything we thought we knew about the nature of life and intelligence. It would be one of the most profound discoveries in human history.
I can't even imagine what that would be like. But while the search for extraterrestrial life continues, we're also still trying to understand the early stages of our own universe. I'm talking about those first few moments after the Big Bang, when everything was a hot, dense soup of particles. How did we go from that primordial chaos to the intricate web of galaxies and clusters we see today?
It's a mind-boggling process, and we're still piecing together the details. We know that gravity played a key role, pulling matter together over billions of years to form stars, galaxies, and those massive cosmic structures. But the exact mechanisms of how those first stars ignited, how those first galaxies took shape, are still being actively researched and debated.
So it's like watching a time-lapse video of the universe evolving, but some frames are still missing.
That's a great way to put it. And to fill in those missing frames, we're using a combination of powerful computer simulations and observations of the early universe. Telescopes like the James Webb Space Telescope are giving us unprecedented views of those first galaxies, allowing us to study their formation and evolution in greater detail than ever before.
It's amazing that we can actually look back in time and witness these early chapters in the universe's history. Okay, so we've touched on early galaxies, but what about the particles themselves? I remember reading about these ultra-high energy cosmic rays particles that are zipping through space at nearly the speed of light, carrying unimaginable amounts of energy. What are these particles and where are they coming from?
They're like the ultimate cosmic messengers carrying information about some of the most extreme events in the universe. We're talking about protons and atomic nuclei mostly that have been accelerated to incredible speeds and energies, millions of times higher than anything we can achieve in our most powerful particle accelerators here on Earth.
So the universe has its own natural particle accelerators that are way more powerful than anything we've ever built.
It seems that way.
That's pretty humbling.
It is. But here's the thing. We don't know for sure what's powering these cosmic accelerators. We know these ultra-high energy cosmic rays are coming from outside our galaxy, but their exact origins are still a mystery. Some of the leading candidates include active galactic nuclei, those supermassive black holes at the centers of galaxies that are gobbling up matter and spewing out enormous jets of energy and gamma ray, bursts, those incredibly powerful explosions that are thought to be the birth cries of black holes.
So we're talking about some of the most energetic and violent events in the universe.
Exactly. No wonder these particles are packing such a punch.
Yeah, but the mystery doesn't end there. There's another puzzle related to these cosmic rays called the GZK limit. You see, when these particles travel through space, they should interact with the cosmic microwave background radiation, the afterglow of the Big Bang. These interactions should drain their energy, preventing them from traveling very far.
Right.
So it's like there's a speed limit for these cosmic rays.
That's the idea. But we've detected cosmic rays that seem to be violating this limit, arriving at Earth with energies higher than they should be able to maintain over such vast distances.
That's like witnessing a car break the sound barrier without even revving its engine. What could be going on there?
That's what we're trying to figure out. There are some wild theories out there. Maybe there are exotic new particles we haven't discovered yet, or maybe our understanding of special relativity needs to be tweaked at these extreme energies. It's a real head scratcher.
It seems like every time we answer one question about the universe, two more pop-ups. But I guess that's what keeps things interesting. Okay, so we've covered these super energetic particles, but now let's talk about something a bit more down to Earth, or rather down to star. Let me talk about the lithium problem. I know lithium is used in batteries and all sorts of tech here on Earth, but what's the cosmic problem surrounding this element?
The lithium problem is a bit of a cosmic accounting error. You see, according to the Big Bang Theory, we can predict how much of each element should have been created in the first few minutes after the Big Bang. And when it comes to most elements, the predictions match up pretty well with what we actually observe in the universe.
Wow.
But there's a discrepancy with lithium. We see less lithium out there than the Big Bang Theory predicts.
So it's like the universe misplaced some of its lithium.
Exactly. And scientists are trying to figure out where that missing lithium went. It could be that our understanding of the nuclear reactions in the early universe is incomplete, or maybe there are processes happening in stars or other cosmic environments that are destroying lithium more efficiently than we thought.
It's amazing how even the abundance of a seemingly simple element like lithium can hold clues to the workings of the universe. Okay, so we've talked about a missing element, but now let's talk about something even more elusive and mind-bending. Hawking radiation. This is one of those concepts that has always fascinated me, but I'll admit it's a bit hard to wrap my head around. Can you give us the Hawking radiation for dummies explanation? I'll do my best. So imagine a black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. According to classical physics, what goes into a black hole stays in a black hole. But Stephen Hawking, the brilliant physicist, realized that quantum mechanics throws a bit of a wrench into that picture. I'm sensing a theme here. Whenever quantum mechanics enters the chat, things get wild.
Oh, yeah.
You're telling me, so according to quantum mechanics, even empty space is not truly empty. It's actually buzzing with virtual particles, pairs of particles and antiparticles that pop in and out of existence incredibly quickly. Hawking proposed that near the event horizon of a black hole, that point of no return, one member of these virtual particle pairs could fall into the black hole while the other escapes into space.
So it's like the black hole is stealing particles from the vacuum of space.
That's a great way to visualize it. And these escaping particles are what we call Hawking radiation. They carry away a tiny bit of energy from the black hole, causing it to slowly evaporate over incredibly long periods of time.
Black holes evaporating. That's wild.
Yeah.
But it makes me wonder if they eventually evaporate, what happens to all the information that fell into them. Doesn't that violate some fundamental laws of physics?
That's the big question, and it's led to what's known as the black hole information paradox. It's a puzzle that has been challenging physicists for decades, and it's forcing us to rethink our understanding of how information is stored and conserved in the universe.
I'm starting to realize that the more we learn about the universe, the more questions we have. Okay, so we've explored these incredible concepts from the expansion of the universe to the mysteries of black holes. But it feels like we've only scratched the surface of what's out there.
We've barely dipped our toes into the cosmic ocean of mysteries. There's so much more to explore, from the nature of dark matter to the possibility of other universes. And with every new discovery, with every new question we ask, we're pushing the boundaries of human knowledge and deepening our understanding of our place in the cosmos.
It's incredible to think about how much we've learned about the universe, But it's also humbling to realize how much is still out there waiting to be discovered. We've talked about all these mind-boggling concepts, but I think it's time to circle back to one of the most intriguing and enigmatic objects in the cosmos, black holes.
Ugh, black holes. Those cosmic enigmas that capture the imagination and challenge our understanding of the very fabric of reality. They're regions of space-time where gravity reigns supreme, warping space and time to such an extent that nothing, not even light, can escape their grasp.
They're like the ultimate cosmic vacuum cleaners, right? Sucking up everything in their path.
Yeah.
But I've also heard them described as like gateways to other dimensions, or even as cosmic recyclers, where matter is broken down and perhaps reborn in new forms. It's all so mind-boggling.
And that's just the tip of the iceberg when it comes to black hole mysteries. One of the biggest questions that keeps physicists up at night is, what happens at the singularity, the point at the center of a black hole where density and gravity become infinite? Our current laws of physics simply break down at that point, so we're left with more questions than answers.
It's like peering into the abyss, the ultimate unknown. But despite their mysterious nature, we're learning more about black holes all the time. right? I mean, we've actually been able to observe them merging, creating those ripples in space-time known as gravitational waves. And we've even captured the first ever image of a black hole shadow.
Exactly. Those observations were groundbreaking, providing us with incredible insights into the behavior of these cosmic behemoths. And with new instruments and technologies coming online like the Event Horizon Telescope, we're poised to learn even more about black holes in the coming years.
It's amazing to think that these objects, which were once considered purely theoretical, are now being studied in such detail. But I guess that's the nature of science, always pushing the boundaries of what we know and what's possible. And speaking of pushing boundaries, let's revisit one of the most fundamental and enduring questions of all. Are we alone in the universe?
The search for extraterrestrial life. The quest to find out if there are other intelligent beings out there in the vast expanse of the cosmos. It's a question that has captivated humans for centuries. And it's one that's becoming increasingly relevant as our technology advances and our understanding of the universe expands.
It feels like we're living in a particularly exciting time for this search, right? We were discovering more and more exoplanets all the time, and some of them seem to be located in the habitable zone around their stars where conditions might be just right for life as we know it to exist.
Absolutely. The sheer number of planets we're finding, the diversity of planetary systems out there, it's truly mind-boggling. And it makes the possibility of life beyond Earth seem more and more likely. But the challenge, of course, is finding definitive proof.
So it's a bit like searching for a needle in a cosmic haystack.
That's a great analogy. And the needle could be anything from microbial life clinging to the subsurface of a distant moon to advanced civilizations capable of harnessing the energy of entire stars. We simply don't know what to expect, which makes the search all the more challenging, but also all the more exciting.
And what are some of the ways we're looking for those needles, those signs of life beyond Earth?
Well, scientists are taking a multi-pronged approach. Some are focusing on searching for biosignatures in the atmospheres of exoplanets, telltale signs of gases that could indicate the presence of biological processes. Others are listening for radio signals from advanced civilizations, hoping to catch an intentional or even accidental transmission from a distant world. And still others are exploring our own solar system, looking for signs of past or present life on Mars, Europa, Enceladus, and other potentially habitable worlds.
It's like we're casting a wide net across the cosmos, hoping to catch a glimpse of something truly extraordinary. But even if we don't find definitive proof of extraterrestrial life in our lifetimes, the search itself is invaluable, isn't it?
Absolutely. The quest to understand our place in the universe, to explore the possibility of life beyond Earth, it's pushing the boundaries of science and technology, leading to new discoveries and a deeper appreciation for the complexity and wonder of the cosmos. And who knows, maybe the next big breakthrough is just around the corner.
Okay, so we've talked about black holes, the search for extraterrestrial life, and all sorts of other cosmic mysteries. But it feels like we've barely scratched the surface of this vast and enigmatic universe we inhabit.
That's the beauty of it. There's always more to learn, more to explore, more questions to ask. The universe is a never-ending source of wonder and inspiration, and the quest to understand it is one of the most noble and fulfilling endeavors we can undertake as human beings.
Well said. And as we wrap up our deep dive into the unsolved mysteries of astrophysics, I want to thank you again for taking us on this incredible journey. It's been a real eye-opener, and it's left me with a renewed sense of awe and curiosity about the universe and our place within it.
The pleasure was all mine. And remember, the journey of discovery doesn't end here. Keep looking up at the night sky, keep asking questions, keep exploring, and keep that spirit of wonder alive. Because who knows what incredible mysteries await us out there in the vast expanse of the cosmos.
Until our next deep dive, keep those minds curious and those telescopes pointed towards the stars.